This is a topic you may have visited in an earlier calculus semester. I teach it in Calculus 2. But when we have an object with a mass m, the tendency for it to cause a rotation about an axis is the product of its mass m and the distance it is from the place where it's rotating. That's called the fulcrum. You can illustrate this very well by putting a heavy object like a dumbbell in your hand and trying to hold it out level from your body. See, it's the weight of the dumbbell times the distance that the dumbbell is from your shoulder's rotating point that makes it hard to hold it there for any length of time. It takes a lot of force to keep it from rotating. That force is called the moment of the mass about some rotation line, and usually in problems the rotation line is considered the x or y axis. It certainly is considered the x or y axis when we're trying to find something called the centroid of a planar lamina. But anyway, if we think of the lamina with variable density, not instead of constant density, variable density, then a small enough rectangular portion of it can be thought to have a constant density, even though we know it really doesn't, but we can assume that, and assume all those mass is concentrated at some point in the interior of the rectangle. The moment of this small rectangular bit of mass is given by this formula. The moment about x-axis is m times y sub k, and the mass of the object is rho times the area of the rectangle. So there's the y, maybe I should have called that, yeah, this is moment about the x-axis yi. Here's how I hope to describe this. We're finding the moment of this rectangular piece about the x-axis, and that moment would be the weight of this piece, which would be the density times its area, times the distance the object is from the x-axis, and that's the yi. So the moment of that particular rectangle is given by this. That's the moment about the x-axis. And the moment about the y-axis, similarly, the mass times its distance from the y-axis, and that distance from the y-axis is xi. So, and the mass is the density at that particular point, even though we assume the whole rectangle has density function that's constant at that point. Even though we know it's not true, we use that for the density of the entire rectangle, and then this is the area of that rectangle. So density times area times distance from the fulcrum, that would be in this case the y-axis, so xi. So forming the Riemannian sum of all those products and taking the limit as the maximum of the delta AI, the maximum of the areas approaches 0. See, that means these rectangles are getting infinitely small. Then we can get the moment about the x-axis as the double integral representing the area. You have the double integral dA, and then this is y, the distance from the x-axis, times of that particular, of any particular point, times the density at that point, rho, at xy. So that's what makes up the pieces of the moment about the x-axis. The moment about the y-axis, similarly, it's the same exact thing, except replace the y, distance from the x-axis, with x, the distance from the y-axis. So now we know how to find the moment about the x-axis and the moment about y-axis for a region R with non-uniform density. And now it gets even more interesting. We can find the center of mass of a planar lamina with variable density, and in Calculus 2 they had constant density. So if the mass of the lamina, and we can find the mass, that's easy, I think I described that. We've actually been doing that. Find the mass of the lamina, so that's what we've been doing before, so that's easy. The only thing that's new is finding the moment about the y-axis and the moment about the x-axis, and that I just gave you formulas for. Moment about the x-axis, remember, has a y in the product, moment about the y-axis has an x in the product. Remember, that's the part that represents the distance from the rotational point, called the fulcrum. And so, if R is a simple plane region, and that means the density function is just 1, then xy is called the centroid of the region instead of the center of mass. And so that's something that we'd already done in Calculus 2, but now we're going to use double integrals and do the same thing. So it's often possible to determine at least one of the coordinates by symmetry, and that is correct, if the density function is constant. You have a better chance of that. But so find the center of mass for the triangular lamina with vertices, the points 0, 0, 0, 1, and 1, 0, and density function rho of xy equals x times y. So the mass of the region is given by this integral, x times y, that's the density function. I have it in this order, dy dx, and I want you to think through this triangle. This triangle has vertices 0, 0, 0, 1. That's if I had an axis here. Maybe I'll put one here real quickly. If I had an axis here, it looks like I have to have something there. Well, so I'll put x here and one minus x here. Now just why am I putting 1 minus x in there? And the answer is that's the equation of the line that connects the point 0, 1 and the point 1, 0. The point 0, 1 here, the point 1, 0 here. I guess this one's kind of wackily, distortedly large relative to what I need it to be. There. The point 0, 1, the point 1, 0, this line has slope -1 and y-intercept 0, 1, so it's -1x plus 1 or 1 minus x. So y goes from 0 to 1 minus x. X goes from 0 to 1. Recalling that it goes, this is 2 here, so x goes from 0 to 1. If I think about drawing stripes across this region, right? Top of the stripe hits at 1 minus x, the bottom hits at y equals 0. See, there's these limits of integration. X going, started drawing the stripes at 0, stop at 1 for x. Okay? So that's pretty much the story on this thing. Okay, and what else we got? Limits of integration, well that's, see if you find this first, then it's pretty easy to include more. And when I say include more, we're going to say, well, this is the, actually you could think of it as the mass of the object, or you could also say it's the volume underneath this curve xy and above that region, and actually above this triangular part. So the line jutting between here and here. And that turns out to be, this integration is too easy, I just let my machine do it. You don't need any help to do that. But I got 1/24. We can do that in pieces if you want, but you know, integrating with respect to y squared over 2, well, I don't think I need to work that out. That's simple integration, so you can probably work that out yourself. And moment about, this was the mass. The moment about the, this would be the moment about the x-axis where we have an extra y. And integrating that with respect to y, you get y cubed over 3. The moment about the x-axis turns out to be 1/60th. And the moment about the y-axis, hey, I don't have that one worked out. Should we do it? Should we do it by hand? Nah, let's not. Integration of a polynomial is not a problem for you. Well, it just turns out to be 1/60th. You know, I really didn't need to do that because if you look at our density function, it is symmetric. So I probably could have guessed that. So then what is our centroid? The centroid is a point x is 2/5, y is 2/5, because I put 1/60th over 1/24th. And when I simplify that, that's about from here. Well, that won't let me do that. So, well, okay, I'll take it from there. So 24/60th, better known as dividing by 12/2/5. So let's see, about 0.4. Remember, we're over this region where this line cuts across like this. So it's actually 2/5. 2/5 is closer to that line than it is in the origin, and we would expect that. We would expect that because there's a little more density closer to that line than there is towards the origin because of the density function xy.